Stand on a beach at high tide. Wait a few hours, and the ocean seems to breathe out. Then it comes back again, often twice in one day, as if the whole sea is on a schedule. The usual answer is the moon pulls on the ocean. That answer is true, but it is also where the weird question begins. If the moon is on one side of Earth, why is there also a high tide on the opposite side? Why does the ocean not just pile up under the moon and call it a day? The answer is not that the moon has two invisible hands. It is that tides are caused by a difference in gravity across Earth. Tiny differences across a planet are enough to stretch water into two bulges. And as Earth rotates through those bulges, your coastline sees water rise and fall. So today, Brain Nest is asking why the ocean rises twice a day. And by the end, the second high tide should feel less like magic and more like geometry. Start with the simplest fake Earth, a smooth ocean world with no continents. Put the moon on one side, and gravity is strongest on the side facing the moon. That nearby water is pulled a little more than the center of Earth is pulled. So one high tide bulge points roughly toward the moon. That part is easy to picture. The far side is where the explanation usually gets rushed. The far side is farther from the moon, so the moon pulls on it a little less. Meanwhile, the whole Earth-Moon system is moving together around a shared balance point. Compared with Earth's center, the far side water is pulled less, so the relative tidal force points outward. So the ocean stretches both toward the moon and away from the moon. That stretch is the tidal force. It is not one giant lift. It is a planet-wide stretch. Now, freeze the picture for a second. There are two bulges and two low spots. High tide happens when your coastline rotates into a bulge. Low tide happens when your coastline rotates between the bulges. Because there are two bulges, many coastlines pass through two high tides in one lunar day. They also pass through two low tides. That is the clean classroom version. But real Earth is not a perfect blue marble. Continents get in the way of water trying to follow the ideal bulge. Ocean basins slosh, resonate, and delay the tide in different ways. That is why tide tables are local, not one global clock that works everywhere. Still, the two-bulge idea is the backbone of the daily rhythm. Once you see that shape, the repeating highs and lows start to make sense. Now for the timing. Why is the tide clock not exactly 24 hours? Earth rotates once in about a day, but the moon is also moving around Earth. By the time your beach faces the same direction again, the moon has shifted a little farther ahead. Earth has to rotate a little extra to line up with the moon again. That extra turn makes the lunar day about 24 hours and 50 minutes. So tomorrow's high tide usually arrives later than today's. This is why tide tables look like a schedule that keeps sliding forward. If you fish, surf, sail, or walk tidal flats, that sliding schedule matters. The ocean is not random, but it is also not synced to your wall clock. It is synced to the moving geometry of Earth, moon, and water. That is why the phrase twice a day is useful, but slightly simplified. The better phrase is two high tides, in most places, during a lunar day.
The moon is the main character, but the sun is not just background decoration. The sun also makes tides, just weaker than the moon's daily effect. When the sun, Earth, and moon line up, their tide-making effects reinforce each other. Those are spring tides, but the name does not mean the season spring. Spring tides happen around new moon and full moon. That is when high tides can be extra high and low tides extra low. When the sun and moon pull at right angles, they partly work against each other. Those are neap tides. Neap tides usually have a smaller difference between high and low water. So the moon sets the main rhythm, while the sun turns the volume up or down. This is why tides change through the month, not just through the day. The daily tide clock is nested inside a monthly moon phase pattern.
Now add real coastlines, and the neap model gets beautifully messy. Some places get two similar high tides each lunar day. Some places get two uneven high tides. And some places get only one high tide and one low tide in a lunar day. That does not break the physics. It shows how ocean basins reshape the signal. A narrow bay can amplify the rise and fall. Shallow water can slow the tide wave down. Wind and air pressure can push water higher or lower than the tide prediction. That is why a tide app can be accurate for one harbor and much less useful for the next coastline over. Tides are global physics filtered through local geography. The simple model explains the engine. The coastline explains why your beach may not look like the textbook drawing. So here is the whole story in one pass. First, the moon's gravity is not exactly the same across Earth. Second, that difference stretches the oceans into two bulges. Third, Earth rotates through those bulges, making highs and lows. Fourth, the moon moves too, so the tide day is about 24 hours and 50 minutes. Fifth, the sun makes spring and neap tides through the month. Sixth, continents, basins, weather, and shoreline shape make local tides complicated. The second high tide is not a mistake in the moon story. It is the clue that tides are about stretching, not just pulling upward. That tiny difference in gravity becomes a daily rhythm big enough to move coastlines. So here is the brain nest question. Which part surprised you most? Was it the far side bulge, the 50-minute delay, or the fact that some places only get one high tide?